As part of the series, I will talk today about wafer-level process technologies for silicon carbide and gallium nitride power electronics. This is a very broad topic, and what I brought with me today are some project examples which cover some technologies we have in-house, we developed in-house, or we developed together with partners. And that's also the point where I want to send out a thank you for everybody who participated in these projects and contributed. So it wouldn't be possible with all the efforts the colleagues added here. So thanks a lot in advance. Next, I would, does it skip? Oh, no, it skips. Next, I would like to give you a short outline about the talk today and what you can expect. So I would like to start with a rough overview from chip-scale packages to multi-chip module integration, highlight some pros and cons of the different packaging approaches, and head over to some examples, 3 examples where we integrate GaN on silicon isolator chip scale package, and then continue to 2 examples of multi-chip modules, GaN integration with or without backside contacts, having 2 different approaches, which I will go into detail a bit later. And then in the second part or the later part of my talk, I will talk about silicon carbide in wafer level packaging. So about the 3D integration or 2.5D and 3D integration, and some slides on embedding in silicon carbide. And I will finally conclude with a summary and an outlook. So let's dive into the first topic, to the general overview about the heterogeneous integration from chip scale package up to silicon fan out, or as we called it here, embedded silicon fan out wafer level packaging. So on the left side of the slide, you will see some approaches where we have the active chip, the RF chip, or the MMIC, whatever it is at the end, mounted to a substrate, and the electrical connection is formed using wire bonds. And within this technology, you will sure find a good thermal connection through the backside of the chip to the substrate, but you will quite be challenged with some high inductance of the wire bonds, and also caused by the wire bonds by the large footprint. In the next assembly technology, we will hand over to flip chip assembled chips, and the chip will be face down mounted on a substrate where we have a redistribution layer, and this again has a better inductance caused by the bump interconnections. For sure it can have a smaller footprint, but the thermal connections or the thermal conductivity might be reduced or is not that good, because we have some interface material which might suffer in its thermal conductivity. When we move on to multi-chip modules and system and package integration, there we are all familiar with the integration of active chips in some mold compound with thin film RDL on top, which then can be also cooled from the backside with an cooling device or just a heat sink. So here again we have a bad thermal connection because the mold compound is not very good in its thermal capabilities. We have the integration is very good, it's okay. We also have very low inductance because of the plating of the redistribution layer, and we for sure can end up with a very small footprint of this device. If we take this approach further, then we will not place the chip into the mold compound, but replace this with silicon. Silicon for sure has much better thermal conductivity than the mold compound, and it will give us a good thermal connection to the outside. And we have all the other benefits we've seen from the fan-out wafer level with mold compound. So again, low inductance and also a small footprint. And for sure, the integration is very high as well. Next, I would like to dive into 3 sample projects we have run here, which will cover some of the technologies presented here and will give you an overview about the challenges and we were facing here. But first, let's give a rough overview. We will talk about the project we have done with the Accent Plus network. I'm sure many of you are familiar with this network. Those who aren't, join this, have a look on their website. You can get some services there over the network, which might help and cover some of your problems you are facing. So in this approach, we have a chip scale package with backside contact. So we started with a GaN device and an SOI device driver. We then applied some polymer dielectric and copper tin silver bumps and thinned the device, which was wafer level, obviously thinned down to 200 micrometer, and then applied some backside metallization with titanium, nickel, vanadium, and silver. In another approach, where we had an embedded silicon fan-out approach with a backside contact, we etched a cavity into a silicon wafer and applied a liner metallization and placed the solder into the cavity. We then picked and placed and reflowed the active chip into this cavity, and with this we were able to polymer embed this chip. So we applied the polymer and filled the cavity, and within had a almost flush mount surface where we then could continue with our redistribution layers and accessing the chip from the front side. And a final metallization with a bump would enabled us to have some flip chip assembly later on. The last example I will talk about is the also a silicon fan-out package, which is possible to do with and without backside contact. And as I mentioned before, in first glance they look very familiar or similar, but actually they are quite different also in this their approaches. So here we probably have a quite thick wafer, and the overall device will also be thicker compared to this one, because here we'll start the cavity etching when we already mounted the wafer on a carrier wafer, bonded the wafer to a carrier wafer. We thin down the wafer and then we etch the cavity. So the cavity itself is has the same height as the chip we want to embed later on. So it will be much thinner. The total device at the end will be much thinner. After we assembled and placed the chip into this cavity, we will polymer embed it. And then we will also could have another grinding and backside metallization so that we are really flush mount. And with this, we can flip the chip again and have some redistribution layers and bump plating on top. So this is the rough overview of the process that I want to show you in the next slides. But we'll start with the first one and dive a bit deeper into it. So this project we were running was a collaboration together with the IMEC, and so the joint research activities within the Accent Plus network. And we had the GaN fabrication done at IMET, and the chip scale package was done here at Fraunhofer IZM. So, as you all know, the state-of-the-art package is we have the die assembly and the wire bond, just like I've shown before. But in order to overcome the disadvantages we have in this challenge, we did, as described before, we had this GaN device on the silicon on an isolator wafer. We thinned this down, and we were able to apply an aluminum nitride ceramic on the backside of the chip with some silver sintering in between. And with this, we had a really good heat spreading and heat removal capability, which we made use of as we applied some heat sink on the backside, obviously making use of some TIM material in between. And this package again was able to be assembled or flip chipped on a second level substrate, some BCB aluminum nitride material. And the part we took over here, as mentioned before, was the redistribution layers and the final bump metallization. So we started with the GaN on SOI. We applied some polyimide lithography, the titanium copper seed layer sputtering. Again, lithography steps, copper tin silver plating, the resist removal, the seed layer edge, and then the grinding and polishing down to 200 micrometer from the backside and applying some backside metallization, which was tin, nickel, vanadium, silver, sputtered, and then finally diced the chip and singulated and generated this chip scale packages at the end. Next, I would like to move on to this project, which was called Smart Power, which had this integration, the embedding integrated in it. And I want to highlight some project details and also some challenges we had to face. So for sure, in such an device, the heat removal and the heat spot management, as you can imagine, is very challenging. And so we made use of this cavity, but we had to find a new concept for the die assembly, because you remember the die assembly was needed to take place within the cavity. And we had also to face some challenges through the RDL implications. Here you see a sketch of the total package schematic. So we have this multi-chip module, and it has some bump connection to the substrate, and it has some heat sink mounted on top. But not only the cavity made us, the cavity in terms of die attach was difficult, but also the cavity geometry is a tricky part in this approach. So you need to very precisely control your die size or know your die size, not only in X and Y direction, but also in Z direction, because as you can imagine, you need to have a very matched cavity to your die size, and the precision needs to be homogeneous around the wafer, so across the wafer. So even if you hit the depth very well in the center, it might be too high or too low on the wafer edge, and this again will make it complicated or make your yield or your assembly more complicated, which will give you trouble. So controlling the die size and the cavity size is very crucial to this approach. Also, the alignment and the plating of the RDL within the cavity or the metallization within the cavity might be very challenging. What I also want to do highlight is that within this package, it is very challenging. The reliability issues are very challenging. So as you can imagine, we have a strong thermal mismatch. We have this GaN device, which is typically grown on silicon or maybe silicon carbide. And we have the chip packaging substrate with all the polymers surrounded it. So this thermal mismatch of these materials and the heat generated in this package might cause some reliability issues one has to face. A possible solution is to integrate a temperature sensor in this package, so you can learn and much better understand what temperatures you are facing, and maybe find solutions for this once you know what temperatures you are facing. The small picture on the bottom right gives you an indication about this multi-chip module system package approach we are facing here. So we worked within 200 millimeter wafers with some cavities, and we could integrate good known dies into these cavities, so which made the yield much better in this approach. Here are some here is the example, the final pictures of the devices we generated. So what you will find here is a large variety of materials. We have silicon capacitors integrated. We have the GaN chips integrated here in the center. We have the temperature sensor integrated. And we have these redistribution layers, which was made out of PCB and copper. One thing I would like to highlight here in this packaging approach is that you will need to really take care of the different material needs regarding the wafer warpage. Because if you are working with all these various types of material, you will earn some warpage of your wafer, and this might become challenging for later wafer level processes. So lithography processes, plating processes, or maybe even just as simple as handling through the machines might be challenging. Another very interesting problem we had to face during this process was the chip shift during the soldering process. You remember that the chip will be placed in this cavity here and will be soldered. So once you solder it, you might have some chip shift during the process, which will have a direct impact on the subsequent lithography process, as you can imagine. So you will need to add some tolerances here to address this, or have a very tight control of your soldering process. On this slide, I would like to give you the final assembly of the device and a cross-section of the device assembled here. So the cross-section here on the left side shows the GaN chip grown on the silicon, which is then soldered on the bottom of the cavity, which we will here have the metallization scheme shown on the bottom. And as mentioned before, you already see one of the problems here. This is not perfectly leveled, but still handleable. But it's a very good example of the challenges I mentioned before. On the right side, you see an X-ray image of the fully assembled system in package here on the right side, and outside some board, and the board assembled too. So we could successfully demonstrate the power RF device with heterogeneous integrated materials and a functional system package by the co-design of the chip and the package, which is very important. Finally, I would like to come to the next project and the next assembly we built and manufactured within the project of Eco2 GaN. So remember, the package approach is a bit different when we start with a thin wafer and etch the cavity into the thin wafer. And what we will end up with is a really thin device. Again, we'll start from the state of the art with the die attach and wire bonds. But if you compare it to this assembly, we will have the silicon frame where the active device is assembled to, and final redistribution layer on top. And this is flip chipped onto a second level substrate, and a heatsink will be attached on top. If we compare those two approaches, you will see that the new approach with the GaN integrated embedded into the silicon have much lower heat spots occurrence, and is much cooler compared to the conventional approach. Here are some examples of the manufacturing of these devices. So as mentioned before, we started with some silicon deep reactive ion etching of the thin silicon mounted on a glass. We etched the cavities, so you see here the cavities. On wafer level, we assembled the dies into these cavities, which can be seen here, and also here in the magnification, you see how these assembled dies are directly located within the cavity of the chip. And after this, we were able to fill all the gaps with polymer and do a frontside metallization and redistribution layer as shown in this bottom part. On the next slide, some cross-section and top image of the final device. So it's a singulated final package here. We have the two GaN chips included here. We have the bumps on top and the redistribution layers in between, and some cross sections as well on the right side. So we have on the right, we have the first GaN chip, on the left, the second GaN chip, and the silicon frame, which is in between with the polymer filling. And you see that the silicon frame has a small taper, which was done intentionally in order to have the life a bit easier during the placing of the GaN chips into this frame. Here's the cross section once more, bigger magnification. You see that we have on the backside, we have the die attach, we have silver sintered on the backside, and on top we have some thick copper redistribution layer with some polymer passivation on top. With this quick walkthrough, I would like to come back to the overview where we started, and ask myself if there's maybe also another thing we missed out. And I think you all know that there is. We missed out all the interposer packaging or assembly techniques. So we could also integrate these kind of chips onto an interposer and make use of 2.5 and 3D integration using silicon, which is very popular and can be found in many devices, or even do it into silicon carbide. And this is really something I would like to talk about on the next slides. What if we do an interposer and not do it in silicon, which is well known, but do it in silicon carbide? And I'd like to shortly motivate this. We all know that silicon carbide is a bit challenging as a material. For sure, we have different grow techniques, how to grow it, how to manufacture these wafers. With this manufacturing techniques like the physical vapor transport and the HT-CVD, we'll face challenges like the wafer sizes are simply not available. We don't have big wafer sizes. I think still standard is 150 millimeter, but and 200 millimeter are available, but very limited and typically only available at the manufacturer side. And it's very hard to get these type of wafers for us as a research institute. Silicon carbide wafers used to face a lot of defects earlier. Now the situation has become much more better and has significantly improved. And in the past year, there was a small bottleneck about the availability of the wafers, and for sure there still is a challenge about the cost of these wafers. But as these there has been a lot of development in the past as well from these wafers. So a lot of research has been done. This can be seen by the amount of publications we will see. And a lot of tool manufacturers also improved their devices, their tools. So the manufacturing, the tools got better and the processes improved. And also the demand and the new markets and investment has been done in the past quite strongly. That's what leads us to that there has been a market. There has been a market demand from EV market, from power and energy supply markets. And this at the end faced some needs or generated some new needs. So the silicon carbide devices needed to overcome. So we started with Schottky barrier diodes, and then this development moved on to some first MOSFET devices. And once we had those devices, it moved on to generating some circuits, and from circuits we will move on to some modules. And all these needs from the market, from the markets, generated again new challenges. On the one hand, technologically, for processing these type of devices and wafers, and for sure in packaging. And one thing which was done earlier in silicon already is that they introduced some interconnections, vertical interconnections in the semiconductor. And I think this is also a very interesting part in silicon carbide, where we need to have some interconnections through the silicon carbide in order to enable 2D, 2.5D and 3D integration of these devices. So having a quick look on the landscape, we all know from silicon manufacturing, through silicon vias manufacturing, we have all these three well-known approaches like via first, middle, and last. And if we have a look whether they are suitable to apply for silicon carbide, then the image changes a bit. But in general, we have the three main processes for generating these wires are similar to silicon. So we have the etching, we will have the need of some isolation in the wire, and we will have the need for some metallization. But there are some additional processes like grinding and temporary bonding. We have to carry those wafers as they get thinner. And these are maybe a bit different to silicon. And within these three main processes, I think the isolation and the metallization are very similar to the ones already known through silicon via fabrication, but the etching is for sure different. And etching silicon carbide is still today is kind of a challenge. So there are possibilities to wet and dry etch this carbide. There's the possibility to laser drill these vias and to do some reactive ion etching. And I think in the past it's became very clear that reactive ion etching is the most promising approach here, because you can really get small vias and very deep vias. So the aspect ratio, very interesting for integrational approaches. As mentioned before, the accessing the via is a bit more tricky than in silicon, because in silicon you can either grind it or release it by etching. Both is possible for silicon carbide as well, but the etching, the uniformity, the etch rate, and the grinding is very challenging. So grinding, typically the grinding wheel for silicon is made out of silicon carbide. So if you want to grind silicon carbide, your grinding wheel will wear quite strong. And you have to consider that in comparison to the metallization, silicon carbide is very hard. So if you want to grind down until you reach the via from the backside, you will definitely face some challenges. In our research activities, in order to use silicon carbide as with interconnections, vertical interconnections, we decided to go for the grinding approach. And on the bottom, you see the results we got. So we started with a small opening until we could open the via totally from the backside. With these challenges, or with these processes established in our institute, we were able to manufacture a silicon carbide interposer. For this, we used the via middle approach and tried out a broad range of via diameters and depth. And we used various types of various thicknesses of isolation in the vias. Typically, we used silicon dioxide. And as mentioned before, we used grinding. And here you see some results. So on the very bottom, you see a silicon carbide interposer, which we generated, which had some interconnections. And we flip chip assembled some chips on it. These are some dummy chips for demonstrational reason, with different thicknesses, different sizes, assembled directly next to each other. And on top, you'll see some cross section of this device. Actually, with this example shown, I want to come back to our overview, where we now kind of talked a bit about the interposer technologies here, and I would like to move next to something which might be still on the right. We see we already have a very nice integration into a silicon embedded into the silicon, the chips. But what if we need some more thermal budget? And this can be realized if we substitute the silicon with the silicon carbide, because as you probably know, silicon carbide thermal conductivity is higher than compared to silicon. It is depending on the crystalline orientation. You can have a thermal conductivity which is equal to copper. So this will be a perfect package if you want to really to get the heat out. And we worked on that in the past years, and I'd like to show you some results. And I would like to compare these results within a mold compound package like we will find it here. So in my next slide, I would like to show you what is the thermal pass through such a package. So we will have the active chip here. We will have some heat sink, some in-package heat sink maybe. it will have a heatsink attached, and then we have TIM material and a heatsink on top. And if you walk through this thermal part, you will end with something like this. And the idea in our approach was to substitute the mold compound material with silicon carbide. And so we came up with the idea of this package. So you will still have the MMIC here in the center, and it's surrounded in a frame made out of silicon carbide, similar to the approach we have seen before with silicon, but now we use silicon carbide. And then we attached a silicon carbide heat spreader, which then was had some tin on it and heatsink attached on top. The results, the analytical results showed that this type of package has a huge potential to reduce the thermal conductivity of this package. So on the left, we compare a standard EMC package, which will have a temperature when we apply a load on it, which will end up with a temperature above 80 degrees C. And if we apply this package, we can reduce the thermal resistance of down to 47 degrees, which is a really massive reduction of this over almost 40 degrees C, applying the same power. But what is challenging is, as I mentioned before, is the manufacturing of this, and especially the etching. So we invested quite some effort in order to make this possible. And the etching was challenging, but what I would like to highlight in this 2 slides of the process flow is how we can embed those chips, these active chips, into a silicon carbide frame and later package. So we start with a silicon carbide wafer. Typically, you get the 4H wafer. Sometimes you still get 6H wafer, which is better for thermal conductivity reasons. We apply a mask. Typically for us, it's a copper etch mask, and then we deep etch the silicon carbide using reactive ion etching. We get rid of the silicon of the mask material and glue it to a carrier wafer. Then, as a next step, we'll grind down the silicon wafer, which cannot be seen clearly here. Sorry for that. We missed. I think we are here's some small bug in the slide. So imagine we'll grind down this from top, and we'll end up with an frame wafer where we just have this part. So with this part, we can take another wafer which holds the MMIC or the active chip and perfectly located on the another carrier wafer and bond those two together. So the MMIC will be located directly in the cavity and surrounded by the frame. We then release the top wafer and can do the redistribution layer on top. We'll stop here and take another wafer, which will be the heat spreader. We'll take the silicon carbide wafer and bond these two together. And once we release the carrier wafer, which we have assembled here, bonded here, we can do the redistribution layers and the bumping on top. What I quickly went over and didn't tell you in detail was this silicon carbide wafer, which was coated with some silicon carbide nanoparticles. Because if you have a look on this package, then here you have a quite hot chip, which needs to pass through this adhesive layer in order to reach the heat spreader, and from there on to some heat sink. In order to improve the thermal conductivity of this adhesive, we filled this with some nanoparticles. And on the next slides, I would like to show you how we did it. So this is roughly the chip and the chip dimensions we were facing. So we had this MMIC, and we etched a cavity in the dimension which was 30 microns bigger than the MMIC itself. And with this, we were able to bond the MMIC together with the frame wafer, and later on fill this with copper. At that stage, we needed to coat this wafer with this adhesive in order to bond the carrier wafer to it. And we got some silicon carbide nanoparticles and mixed them with the commercially available PCB. So we developed a process where we can fill up to 37 weight% of silicon carbide nanoparticles into PCB and steer it heavily. So we end up with a black PCB solution, black PCB polymer. And then we were able to coat it onto these wafers, and we can clearly see that this silicon carbide wafer, which has been coated with this nanoparticle filled PCB, turns black, obviously. And once you have assembled your heat spreader wafer with these silicon carbide nanofilled PCB wafer onto your frame wafer, you can build up the final metallization, and you will achieve this new packaging approach I just discussed. And with this quick walkthrough, I would like to come to my summary and just review what we've seen in the past few minutes. So we have had a look on the different module integration possibilities, from chip size package to multi-chip package system package integration. We had some details on the silicon fan-out wafer level packaging possibilities with and without backside contact with various approaches. And we had a short look into, I think, newer developments where we use silicon carbide in wafer-level packaging technologies, where we think about 3D integration and also into embedding into silicon carbide. And with this and this extended overview, I would like to end my talk and thank you for your attention, and would like to open the stage for some questions.